Ready? Good afternoon and welcome to lesson 11 of the course on industrial automation and control. So far we have learnt about sensors, but before learning about actuators, I thought that it'll be more useful to learn about automatic controls, mainly because of the fact that several actuators are actually closed loop control systems themselves. So it is useful to learn about automatic controls before learning about actuators. So we'll start with automatic controls and go on for that for a few lectures and then eventually come back to actuators. So here we go. This lecture is on introduction to automatic control. So we are going to discuss some basic concepts and finally look at the basic structure of a controller called the PID controller, which is almost it is said that 90 to 95% of all industrial continuous controllers are PID controllers. So we are going to have a look at that, why that structure of the controller is so useful. So that's the purpose of our lecture. So let's see that in greater detail. So as we usually do, let us look at the instructional objectives of this lesson. So after this lesson, one should be able to define the performance objectives of automatic control, what basically automatic control wants to do. He or she should be able to define what is basically describe what is stability and three causes of instability which are very typical in a process in an industrial process control loop. Should be able to define a very important performance indicator called the steady state error and basic strategies or philosophies of reducing steady state error. And while doing it, and of course the other objective of automatic control is how to get rid of the disturbances, or rather how to tackle the disturbances in the sense that how to reduce the effects of the disturbances on the output. And all these, as we shall see, will naturally lead to a kind of control structure which is known as PID control. So this is what we wish to learn today. So let's go ahead. Let's first look at the automatic control objectives. What does an automatic control loop basically does? So here is an automatic control loop, well known to us because most of us have already had a course on automatic controls. So here is the set point. Here is the set point. Just a moment, let me select my pen. So here is the set point, and this is the controller, this is the actuator, which as we have discussed, which increases the control energy and finally gives input to the plant. This is the plant itself, this is the output which we want to control, and this is the feedback through the sensor. This is the what is known as the error. So what's the objective of automatic control? The objective of automatic control is firstly to maintain stability. What does it mean? It means that if we want to hold a particular hold the output at a particular level, we should be able to hold it. It's not that the output will run away, or it's not that the output will oscillate. So we want that quantities reach certain values and stay there. That is roughly called stability. In this course we are not going to have a very mathematical look anyway. So that's the basic idea of stability. So we want that signals in the loop should be stable, it's not that they should be continuously moving around. That's a very important objective of automatic control, especially for processes which are inherently unstable, this is a very important objective. Without this we cannot run the process at all. The next is to we can ensure that we can hold the outputs at a certain level wherever we want to. We want the output to follow the set points, that is we want that the output will follow the set point. Now the set point is, as we have noted, it is a function of time, and this output is also a function of time. So we would like that this function of time resembles this function of time as closely as possible. So how do we express this closeness? We express it in terms of, typically this set point generally very often are step functions of time, that is they change over time like this. So this is a typical, this is R T and this is T. So they take step jumps, again are held. So we are typically talking of this kind of step responses, this kind of set points. So we, with respect to this kind of set points, to express the degree of accuracy with which y can be close to R, we express various quantities like the steady state error, rise time, settling time, etc. We will have a more detailed look at these. So this is the second basic important point, follow the set point. The next important point is, of course, to reject disturbances. That is, even if the output once comes close to R, there are several external signals which are working on this process, which are not in our control. So there are output disturbances or load disturbances which occur very often. There could be input disturbances from the actuator. For example, we shall see that if you have a hydraulic actuator, then one of the main things that happens in the actuator is basically an amplifier. It amplifies power. So anything which amplifies power usually has a power source. So for example, the hydraulic actuator has an oil pressure source. Now if the pressure of the oil changes, that would be an input disturbance to the actuator. Similarly, if you take manufacturing, then what happens is that, for example, suppose you are taking rolling. So in rolling, what you want to do is you want to control the speed of the rolls and the gap of the rolls. Now when a metal bar comes and here are the rolls rotating, so when it comes and grips the roll, immediately there is a tremendous torque demand which comes on this. So that torque demand depends on a lot of factors. For example, one of the important things on which it depends is the temperature of the bar which is biting into the rolls. So such things are called load disturbances. Similarly, anything we want to sense, we are going to have various kinds of measurement noise, bias, right. So electromagnetic noise, electrostatic noise. So they are the feedback disturbances. So there are various kinds of disturbances which are acting on the loop all the time, which tend to move this output away from R. So the job of the controller is to every time it moves away from R, the job of the controller is to generate suitable input such that it comes back to R. So thereby rejecting disturbances. So that's the other prime objective of automatic control. So maintain stability, follow set point, and reject disturbance. These are the three major objectives of automatic control. So having seen that, let us look at see in some detail the concept of stability. So let us make some comments on this concept of stability. So first is that when do we have instability? We have instability when cause builds effect and effect builds cause. right. So, for example, suppose there is an typical case. Let me give you a simple example. Suppose you have an inverted pendulum. So, a pendulum which is held here on a hinge, right. So, if the pendulum is vertical, it is suppose just maintaining its position. Now, if you give it a little push, if you give it a little push, let us say this side, then the pendulum will come to this position. So, here is a cause which produced an effect of an angle. Now, due to this effect, now the gravity force which was acting vertically down, now it has a component this way. So, now due to this component, this pendulum will move further and will come to this position. So, you see that here is a cause which built an effect, that effect generated a further torque. So, it generated further cause which generated further effect, and therefore, this is not a stable position, this is an unstable position, right. So, this is the basic phenomenon of stability, and this phenomenon demonstrates itself in various ways in case of flows, temperatures, motion, displacements, every variable, right. So, this is the basic concept of stability. So, what is the next point? Then what is the unstable response? I mean, how is it typically characterized? For example, take the case of, there are two typical demonstrations of an unstable response. For example, in open loop, if the plant is not operated in open loop, then the output saturates to a stable operating point. What is a typical example? So, a typical example is, suppose we have the case of an induction motor torque speed curve. Okay. So, this side is speed and this side is torque. As electrical engineers, we have studied this. So, the torque speed curve typically looks like this, right. And let us say that a load characteristic looks like this. So, as the speed increases, the load torque demand also increases. So, now if this load this is the load torque speed characteristic. So, now if the suppose we connect the motor to this load and then switch on the motor, what is going to happen? Say initially in this case, of course, the motor will not start because of the fact that this torque is larger. So, actually what we have to do is that we will assume that the torque will come here. Right. The pen, oh, I see, I have to touch it here again, it is in the eraser mode. I have to touch it to the pencil and then I have to touch it to the color, correct. So, suppose the load characteristic goes like this and the motor characteristic, rather than that, right, suppose the motor characteristic is through this path, motor characteristic is this. So, now if you consider this operating point, then suppose here the motor torque and the load torque are same. So, it's a stable operating point, motor is generating enough torque which the load demands, but if the speed here is slightly changed, let us say this way, and if the motor goes to this position, then what happens now is that the generated torque, which is this one, is more than the load torque which is given by the green curve. So now you have extra torque. So now this extra torque will do what? It will increase the speed of the motor. So now the motor will go to this point where it has further extra torque, then it will come to, finally it will eventually settle at this point. So you see, at this point again the motor torque, generated torque, is actually equal to the load torque, but in this point now if something increases the speed and it comes to this point, my dot is getting shifted. Now what happens is that if the motor shifts from this point to this point, immediately what will happen is that the generated torque will actually fall below the load torque requirement. So the motor will tend to go back to its old operating point. So actually this is the difference between a stable and an unstable open loop operating point, that in an unstable point, if you move it away from it, it tends to move farther away from it and finally settle to a stable operating point. This is what the motor is doing. On the other hand, if you, from the stable operating point, if it moves away, it is going to come back to that operating point. It will not move away, right? So this is what is going to happen. This is what I mean. Now what happens is that, but this tendency, but you can always, if you use a controller, one of the jobs of the controller is to operate a plant around unstable operating loop points. That is why control is used in many cases, for example in process control, in aircrafts, and also in motor. So what this will do is actually that, taking the old example, now if the torque speed curve is around this point, then here if it is operating, then now the control, now if it tends to move, it will tend to move away, but now the controller will actually, what the controller will do is that the controller will control the, let us say, the motor terminal voltage, and it will actually reduce the torque so that it comes back. Again when it comes back, it will have a tendency to move this way, and then it will have a tendency to move this way. So again the controller will move it up. So under control, this tendency of the this tendency of the open loop to actually saturate to a stable operating point is actually prevented by the controller. So every time from an unstable loop, it will tend to go to the stable point, but the controller will push it back, then it will tend to go to the other operating point, and then the controller will again push it back. So this is what happens. So the plant tends to run away and the controller keeps pushing it back, so you have an oscillating response. So usually this is typically what happens when in case of an unstable response, that the closed loop output shows sustained oscillation. So that is also a kind of instability. So this is typically what you find when you operate a plant in either open loop or closed loop. So and you can draw examples from exothermic reactors where temperatures tend to run away, aircrafts where aircrafts are very often unstable, or you can have motors like the example that I have given. So what I have said is that you can still operate a plant around an unstable operating point using negative feedback. Basically that is what your feedback control achieves. It operates the plant around the unstable point, I mean the point which was unstable according to its open loop characteristic, it can operate it there stably with feedback. However, it turns out that sometimes feedback can turn positive because of various factors like phase lags. So it is when feedback turns positive, immediately at that time we start having oscillations and other symptoms of instability. So this is what, qualitatively speaking, this is what typically happens. So now let us look at three major causes of instability in feedback loops. How does it occur in a feedback loop? So what are the causes of feedback in this instability in this loop? there are two causes, as we know that stability or rather instability is caused by two things. Firstly, that the total phase lag around this loop must be less than 180 degree, because otherwise if it reaches 180 degree, then at that point negative feedback becomes positive feedback, right. The second point is that, but just having 180 degree phase shift is not enough, we should have enough loop gain, that is the cause must finally increase the effect and the effect should also increase the cause. So for that what you need is that you have a high enough loop gain. So these are the two major reasons. One is that the phase lag should be less than 180, more than 180 or 180, at that frequency actually oscillation starts, and the gain at that frequency should be high. So now what are the causes? I mean, how can phase lag increase? So phase lag can increase in many ways. For example, if the delay between the sensor input and the plant output exists. For example, you see previously you see that we were taking the output from here, but for some reason if you take an output from such that there is a time delay between this signal, which is the output you want to control, and this signal, which is the signal you are feeding back. So there is a delay of, let us say, t seconds, then in that case that delay can easily generate instability, and this is one of the prime causes of instability. So that is something. Next is, oh just a moment, yeah. So what's the, similarly there could be delays between controller outputs and plant inputs, right. So very often happens, so there could be a delay, there could be a similar delay block at this point. Then also there is an overall delay. Basically what every time we have to see that what is the delay or phase lag between this point and this point, that is the loop phase delay. So it could be here, it could be here, even it could be here, it could be at any point, or it could be even in the sensor. You know, sometimes automatic controls processes, even sensors like you have things like online analyzers, where there could be a considerable delay, that is this delay actually occurs in the sensor. It is not in sensing the input, directly from here it is fed, but this unit causes a time delay, that is also possible. So anywhere around this loop if you have delay, it is a potential cause of instability. Next is, and apart from delay you could have various kinds of time constants in this process. For example, you could have time constants in, actually time constants always exist. For example, the sensor, we often take it as a unity feedback, but it is never exactly unity feedback, it has its own time constants, also because of the fact that the sensor is actually generally placed in a housing against jackets. So such things cause time constant. Similarly, an actuator, though we sometimes in our idealized view we sometimes think that the controller output directly goes to the plant, but it actually does not go to the plant. It goes through a power amplification in the actuator which induces its own delay. There could be delays there are always delays in the plant. So these time constants and delays also cause instabilities. So these are the major causes of instability in a process loop. So having seen that, so now we have to take care of these and design a controller appropriately. Now let us look at performance. So what is the first requirement of performance? The first requirement of performance is that performance can be divided into two types in control. One is called steady state performance, another is called transient performance. In general, steady state performance is much more important than transient performance, simply because of the fact that that performance holds over a much longer interval. Generally in industrial automation, the set point changes somewhat infrequently. For example, if you take a power station boiler, then its set point over a day will typically be changed 7, 8, 9 times, maybe less. So when you will have load coming in the morning, its set point will be changed. When lighting load in the evening will start going down after, let us say, 10 o'clock or 11 o'clock, load will fall, at that time you have to reduce the set point. So there are infrequent set point changes, and in between these set points are generally maintained. This happens for a lot of process equipment. So if you have performance degradations which are persisting during that phase when the set point is held, then that is generally considered much more serious than errors that can occur when the set point is changing or immediately after that time for a short duration. So we would first like to ensure steady state performance, and the major consideration for that is steady state error. That is, we want that R should be equal to Y, at least in the steady state. Obviously, if R suddenly changes, Y cannot suddenly change. So Y will have to Y will take some time to come to the level of R, but once it comes, we want that this error will be 0. We want 0 steady state error. This is our wish. So how to obtain that, right? So for that, so we want that this is the steady state error, that is limit of t tending. Typically we take a unit step response. So if the reference input suddenly changes, then how is, as time passes, does the error go to 0? That is limit of t tending to infinity et. We can also express it in a frequency domain form, which says that, which uses the final value theorem of Laplace transforms, and which comes down to the fact that E steady state is limit of s tending to 0 1 by gs ks, right. So so this is the steady state error, and we have to ensure, one of the prime requirements is to ensure by control that this goes to 0. So how do we do that? So we have to control for 0 state steady state. Let's take the simplest case of proportional control. The problem of proportional control is that if you want to, proportional control is just you have a simple gain, and if you get an error of 1 volt, you generate maybe an output of 100 volts. If you get an error of 2 volts, you generate an output of 200 volts. So just simple multiplication. Now obviously we want to, what do we want? We want that this R be equal to Y. So we want to, R is a certain value, so we want to maintain a certain value of Y. Now naturally it happens that for maintaining a particular value of Y, we need a particular value of U. So for the time being, assume that this is not there. So now how are we going to get this U? If you want to maintain this U, then we have to maintain a particular value of E. So unless we have a certain amount of steady state error, we cannot generate U, and therefore we cannot generate Y. So we cannot make steady state error at 0 ever using proportional control. That is what it turns out to be. So what happens is that there are two things that could happen. Either you could artificially increase this R, that is, if you want, let us say, an R of, really want that the output stays at 1 volt, you give an R of maybe 1.1 volt. Just what volt you have to give, that you have to calculate, but so you artificially increase 1.1 volts, so that here you get 1 volt, which is the real output you want, right. Or what you could do is, apart from what the controller is doing, you can give what is known as this manual bias. That is, you apply some additional input right directly to the plant. So you do one of these two things. In that case, you can maintain whatever output you want. But what's the problem? The main problem is that who is going to give this input? How do we know by how much? For example, if we give 1.1 volt for 1 volt, how do we know, let us say, if we want an output of 3 volts, what output we have to give? By how much? So naturally it should not require a manual manipulation. It should be done automatically, right. So that brings us to the question that how can we automatically generate this bias input without any manual intervention. So, the question is that how to create bias input for 0 error, right. So, that is the situation described here. What should be this? So, we see that what is the device which for 0 error gives an output. So, that device is actually an integrator. So, somewhere in the loop there should be an integrator, then even if the error is 0 we will be able to give a finite output. So, there are actually two cases in which an integrator is required. So, the first case is this one. So, if you have an integrator here, imagine that I have written Ki by S in Laplace domain notation, which means that this is actually an integrator, that is u is equal to integral Ki et dt. So, this is the integrator. So, this is equal to ut. So, now you see that even if after some time this at this point even if we get e goes to 0. So, for example, suppose the error goes to 0, this is y, this level is r, this is the level. So, here error is going to 0, but what will be the value of the integral? What will be the output of this block? The output of this block is going to be the area under the curve, because this is the error, this is y and this is r. So, r minus y is this vertical distance. So, this is the area, right. So, this area, even if the error remains 0, this area remains finite. So, you can generate a finite u even when the error is 0, you can keep generating it. So, having an integrator helps. There is another case in which you can have an integrator, that is the integrator is actually part of the plant itself, which means that to be able to sustain an output, the plant may not need an input all the time. So, the plant itself is an integrator. What is a typical example of this? A typical example of this is a tank. So, suppose you have a cistern, like we have in our toilets. So, you can have a flow in, and this flow in is actually, this flow is actually proportional to the level. Actually, there is a, if you might have noticed, if you have looked into the cistern, that there is a ball cock, floating ball. So, when there is no water, then the ball cock is hanging like this and water flowing. So, as water rises, so the ball cock goes up, and at a certain level the valve through which the water is flowing will actually close. So, at that level it will be maintained. So, you see now, so this tank is a plant which this tank is a plant which has an integrator with respect to flow, because the level is nothing but an integral of flow. So, at some point to be able to maintain a level, this is a level, it does not need any flow. So, the flow can go to 0. So, still, so we are having a simple proportional controller. So, the error going to 0, flow goes to 0, but still level is maintained. So, this is another situation where you can have 0 steady state error. Now, so exactly this is what happens. So, now you see, if you put the integrator, what happens is very interesting. So, what happens is that this bias input which was previously coming now comes automatically. That is the integral output which I was talking about now increases till it can, then it goes to 0, and then if you change the set point again from here to here, again some error will be created and it will again integrate and will generate just enough output such that it can be sustained without the error. So, you see that the integrator actually works as a very interesting thing. it actually gives a bias input, but which is not manual. So the bias input, the integrator is actually exactly like the bias input, but it generates it automatically. You don't have to give it you don't have to give it manually, and it will adjust itself depending on depending on the set point. So the integrator will automatically build up and give enough additional input such that at 0 error it can be sustained. So that's the principle by which 0 steady state error is obtained. Now only thing is that now this has certain there are certain drawbacks too. For example, let us see that if you give a step response, then how does it work? How does the loop work? So you see that suppose the process starts from here. Okay, so the process starts from here and starts. So as you have given, so here there is a lot of error. So the proportional controller now generates a positive input which drives the plant. So the plant goes up, and typical we are likely to get a step response like this. So what happens during this phase? During this phase you have proportional is positive, error is positive, so output is positive, but since the error is decreasing, so the output is going down. So it is positive but going down. That is the output of the proportional controller. What does the integral controller do? The integral controller is also positive because it is integrating positive error, and it is increasing because the area, as it is going with time, this area is continuously increasing. So it is positive and going up, increasing, right? So what happens at this point? At this point error is 0. So the proportional controller output is 0, but because the integral controller output is still positive, so the plant continues on this journey in this path, right? Now when it is here, let us say when it is here, the proportional controller around this point P is negative, but I is still positive because of the fact that there is already a large positive integral accumulated here. So here integral is negative, this part of the integral is negative, but still there is a large positive integral. So the overall net output is maybe still positive, so it continues on this journey, but eventually this integral value also reduces and the proportional controller value also becomes enough negative. So the overall input turns negative and the plant turns to move. Now again the same thing happens here. Once it crosses this line, now again it will oscillate. So you see that typically because of integral control there tends to be an oscillation. So there tends to be a high overshoot and an oscillation. So this is a drawback of integral control, that is, to gain steady state error, to gain 0 steady state error, this is the price that you are paying, that in your transient response you are likely to get some overshoot. So that is the picture for the step response. So we want to improve transient response without sacrificing the steady state error. So if we want to do that, then what we have to do is that around this point only, here we have to keep braking, we have to keep braking and around this point so that we can quickly turn. So what happens is that here now we have to slow down. So slowing down means during this phase we have to create more negative input which will grow towards this point. As it comes closer, it should this negative input should increase. Similarly, around this point this negative input should also keep increasing so that it quickly turns, and then actually it will settle very fast. So, you see it will not oscillate. If you, we want that it does not oscillate so many times, but rather follows this yellow curve, maybe does a small overshoot and then immediately settles down. This is the kind of curve that we want. So, now it turns out that this kind of curve we can obtain if we add a derivative term to error, right. So, we want to reduce rise time. What is rise time? We want to reduce rise time is we want to reduce this time. We want to, typically speaking, we want to reduce overshoot, that is this height, and we want to also reduce settling time, that is total time taken for it to come to a steady state. So, we want to reduce that, all these. Now, getting all this is somewhat difficult, and that is why you need to have a non-trivial tuning exercise to come to a compromise between these. Because typically what we do is, it turns out that these things can be achieved. We have already discussed proportional and integral controller, and we have also seen that adding a derivative will try to break so that it does not go towards much overshoot. So, we need a proportional controller, because if you do not have a proportional controller, then there will tend to be too much of oscillation. We need an integral controller to have 0 steady state error, and we need to have a derivative controller to have low overshoot and fast settling time, and we need to tune these gains Kp, Ki and Kd nicely, so that we get a good transient response without sacrificing on the 0 steady state error. One thing interesting to see is that this, so we now calculate input like this. Now, interestingly, that you see that in the steady state, the total E is 0, so therefore this term is 0, so the proportional controller is 0, and since E is not also changing, so there is a d dt is also 0, so that is also gone. So, we only have the whole output coming from the integral part. So, the 0 steady state error concept that we have studied for the integral control holds. Now, so as I said that we need we are looking for a step response like this. This would be a very good step response, and we, if we can make it even sharper, even better, but generally if we want to make it sharper, then if we can make it like this, even better. So, this is a good step response that we would like to achieve. So, now come to the point of disturbance rejection. So, what is the disturbance response? The disturbance, so let us talk about, there are several types of disturbances, and you can do the same kind of analysis, but the most predominant disturbance which occurs generally is the load disturbance in a process, occur due to various reasons, property variations of materials, variations in power sources, voltages, variations in pressure sources, all sorts of things. So, it turns out that the transfer function, we want to reduce the effect of d0 on y. So, what is the transfer function between y and d0? That turns out to be this. So, now again we see that if we have, so it is not possible to exactly neutralize all kinds of disturbances, but let us say one of the major kinds of disturbance is step disturbance again, that is disturbances which change once or twice and then stay on. Okay. So, if you have step disturbances, then you can again see that that if you have an integral, then this term will actually go very high as s tends to 0. So, the effect of, so but for the same reason exactly similar transfer function is coming. So, the same reason why E goes to 0 with integral control, if you put integral control, even the effect of step disturbances will also go away, because the integral value will rise and it will provide the additional torque to actually take care of the disturbance. So, it will produce the integral will rise, and it will here it will, instead of producing y, it will automatically produce an output y plus d0 or rather y minus d0, so that after plus d0 you will get the desired value of y. So this is going to happen. So integral control is one of the major ways of reducing disturbance response. So this is now let us look at some other issues. For example, we have to actually remember these things, because they are very practical issues, and we possibly did not learn about these in our earlier controls course, where we treated things rather ideally. But we must remember here that some other non-idealnesses exist. For example, there can be very often there can be actuator saturation, that is the characteristic of this is the control input Ci, and this is the plant input Pi. So this is the actuator characteristic. So as you increase the control input, the actuator will also proportionally include the plant input, but only up to a certain point, after which it will saturate. So if you give more and more control input, it will not give you proportionally high plant input. So the actuators typically will saturate. Now when the actuator saturates, effectively the feedback loop is opened, because the effect of the error no longer transmits to the output, or rather the plant input. So the input does not change in response to the error, but is held constant. That is the case of an open loop operation. So your control is gone, and not only that, sometimes, as we shall see later, that persistent actuator saturation has very bad effects on controllers, especially because of the fact that controllers have memory. So this is a particular phenomenon which occurs in PID controllers, and we are going to take a look at it in great detail in the next lecture. So next issue that we should look at is sensor bias. So remember that if you have a sensor bias, sensor has errors, then sensors are the eyes of the controller. So whatever the sensor sees, that the controller simply works on that. So if you have bias, you will think that is the controller will produce an input which will have 0 error, but actually there will be non-zero error. So that's so you have 0 error, but you have non-zero error. Similarly, we have to remember that you always have, actually you design controllers based on some models, but it always turns out that these models are actually inaccurate. So you are always going to have model errors, and these model errors are typically dominant in the high frequency band. And now remember that if you have inaccuracies in the high frequency band, it is the errors in the high, actually typically instability occurs in the high frequency band, not in the DC band, lower frequency band. So if you have modeling error in the high frequency band, then such modeling inaccuracies can also lead to stability problems. So we have to remember these things. So to take care of these things, various kinds of other architectures are possible than what we have, that is the loop structure, what feedback we will use, how we will use the controllers, and we will see some of them. For example, feed forward configuration, cascade configuration, we will see all of them. So they are possible. Finally, while we are moving towards the conclusion, let me mention some of my pet facts about control in colloquial terms. So I say that what you feedback is what you control. So the controller exactly tries to maintain the feedback. So if your feedback is erroneous, then your control is erroneous. If you are sitting in the middle of the room and if you are put your temperature sensor at the roof of the room, then you are controlling the temperature at the roof of the room, not in the middle of the room, right? Then what you cannot actuate, you cannot control. So you may be giving whatever in output from the controller, you may be using a fancy algorithm, but if you cannot actuate it, then you are not controlling it. If you can measure or estimate the disturbances, then you can compensate them. So there are many advanced algorithms which precisely try to do that. stability is basically stability is not enough. Stability is barely basic performance. You must ensure stability and then ensure performance. But while you ensure performance, if you as you try to go more and more, drive more and more and improve performance, eventually instability results. So instability is actually generally decides the maximum performance that you can achieve. And models are always approximate. Most systems are actually nonlinear, but that does not mean that we can work with approximate. So linear control can work very well for nonlinear plans, but sometimes nonlinear control may be working better, but 95% of industrial controllers are linear. So we have come to the end of the lesson, and let us review quickly. So we looked at the objectives of automatic control: maintain stability, follow set point, reject disturbance. We looked at stability and found the causes of stability in causes of instability in a process loop. We looked at steady state error and the ways of reducing it, and we also looked at the ways of reducing transient performance, keeping the steady state error at 0. So we saw that the PID control is a very effective way of and simple and effective way of doing that, and eventually we saw that PID control can also do some amount of very common disturbance rejections. So that's the end of the lesson. Here are some points for you to ponder. First is that state the 3 major objectives of automatic control, which I have just now said. State 3 major causes of instability in a control loop and give, this is tricky, try it, give an example for each case, practical example. And is it possible for a proportional controller to achieve 0 steady state error? I have already explained an example. You try to explain it in your own language, and explain how a PID controller can achieve good transient performance as well as 0 steady state response. And finally, justify or contradict the statement that PID control achieves 0 steady state error with step set points and disturbances. Thank you very much. We will see the next lecture. Good morning and welcome to lesson 12 of this course on PID control. So as usual, before starting the course, we will review the instructional objectives, and these are, firstly, that we will learn how to define the related parameters of PID control in an industrial context. Secondly, we will describe and explain in detail about a phenomenon which many times occurs with PID control, known as integrator wind up, and the ways of reducing that. We will describe various ways of implementing the derivative control part. We will also describe the one technique of bumpless auto manual transfer, that is when the control is transferred from auto to manual or manual to auto, so that it can happen without any shock to the process. And finally, we will describe digital implementations of PID control. So in other words, we are going to look at various practical aspects of PID control today. So let us begin with the PID equation. This is the PID equation which we have seen in the last lesson also, where Kp is the proportional gain, or sometimes this is not proportional band as written, but it is proportional gain. But a very similar parameter called proportional band is also used in the context of PID controllers. We will see soon how it is related to the proportional gain. Next is the parameter Ti here, which is called the reset time, and expressed in a peculiar sounding unit called minutes per repeat. This is another way by which an anti-reset wind up scheme can be implemented, typically in hydraulic and pneumatic controls. Now, we will look at a phenomenon, another problem which occurs typically with integral control, and that happens when you have auto manual transfer. Now, let me first explain this term. There are many, most processes will also allow the operator to give input. That is, if he wants, then in certain situations you can bypass the automatic controller, and rather using some input device like a potentiometer or a knob or a switch, you can give manual input to the plant and you can slowly build it up, and then maybe for some purpose, right. So, you might like to write yourself the definition of proportional bands, integral, derivative times. It is, you would like to explain the factors that cause integral wind up. So, integral wind up is basically caused by two factors. So, what are those factors? And we have discussed in this lecture two control architectures which will avoid integral wind up. So, how to avoid that? And then we have seen that while you are implementing derivative control, you have to take care of 2 points such that you do not add unnecessary disturbances and shocks to the plant. So, what are they? And finally, we have seen that a PID controller may be realized in what is known as a position form and a velocity form. So, you need to think how to distinguish between them when which one is required, and also what is the bumpless transfer and how it is achieved. So, the answers to these questions exist in many textbooks and also within this lecture. Thank you very much.